Morning, everyone. I'm Piers O'Hanlon. This is Ravishankar, Borgaonkar, and we've been working on something we've dubbed the Wi-Fi-based IMSI catcher. And so we're going to take you through just a quick overview of what we're going to cover in the presentation. So firstly, just for those of you who aren't aware, what is an IMSI? And then we're going to talk about conventional IMSI catchers. IMSI is basically just the identifier that's inside, that identifies a subscriber, the International Mobile Subscriber Identifier. And there are conventional devices that have been around for a while, ones with sort of trade names like Stingray, that sort of work in the mobile spectrum. But our approach operates in Wi-Fi, and it basically exploits two issues, two sort of functionalities within the way that mobiles, basically smartphones, but can be other devices, automatically connect to Wi-Fi networks based on their IMSI, and also another technique that's based around when devices connect to the sort of operator services for Wi-Fi calling. So then we're going to talk about mitigations for the operator vendor OS, user mitigations, and then a demo. So what is an IMSI? It's basically, as I said, International Mobile Subscriber Identity. It's typically a 15-digit number. The first couple of digits indicate the country code, and then the next couple, well, the first three actually, country code. Next two or three sometimes, depending on where you are, indicate the mobile network provider, in which case, this one's just a kind of made up one. 234 is actually the UK code, and 12 is some kind of rail track one, but it just happened to be 1234. So I just put it in there because what I've done in the demo, I've used that same IMSI as the kind of demo IMSI because I don't want to be splashing real ones around. Then it basically allows for the authentication of a device to the network. It's the identifier. It's like your username in a way. And then that then allows the phone and the operator's databases to then index your secret key, which they both have a copy of, and then do this network authentication procedure. And it's typically stored within in two places, basically, inside the SIM card in the phone, and the IMSI can actually be read off of the actual SIM card using like a SIM reader, one of these little cheapo sort of things, or you can spend a lot of money, but basically it's pretty straightforward to read an IMSI off of a SIM if you actually got it in your hands. But it's generally another story if that's you sat on a device and you want to try and find out what's the IMSI of like that sort of this mobile phone here, like sitting on the desk. But this is what we've, the technique we've developed to do that. Then also inside the SIM card, there's the secret key, which is kept secret. You can't access that. You can't just sort of say, plug it into that reader and say, give me the secret key. It doesn't happen. It's kind of protected. You can basically just you can send it a random number and it'll then carry out some algorithms to do the authentication challenge. But then it's also stored in the operator, so they clearly need to have it to verify that it's a legit subscriber. So it's also an identifier that can be used for tracking. So it's a fairly unique identifier that basically is tied to the subscriber, tied to the SIM, and typically people don't change their SIM very often, so it gives you a good idea of who it is. But there are also a bunch of other identifiers associated with most smartphones these days, like Wi-Fi, Bluetooth, NFC addresses like the MAC address. Although, as you may be aware, there have been moves to make the Wi-Fi MAC address a bit more elusive. iOS introduced MAC randomization on Wi-Fi probing. I think in iOS 8, and then they've taken it slightly further forward. Windows Mobile introduced it, and Android is bringing it in as well. And then there's other device identifiers that are more associated just purely with the mobile phone, the IMEI, the International Mobile Equipment Identifier, which is actually just tied to the actual hardware of the device. It never changes. In fact, it's kind of illegal to go changing that identifier. But that can also be tracked with some of the conventional IMSI catchers, do a downgrade attack, and then you go into a 2G attack, and then you can extract the IMEI. And then there's what's sort of technically known as the MSISDN, which is actually just like your phone number. That potentially can also be used for tracking, but that's typically not that easy to get hold of. Although there are sort of subscription services out there that allow you to look up an IMSI and then potentially find out what the corresponding numbers are. Some of these are probably in a bit of a gray area. So now I'm going to hand over to Ravi, who's been working in the conventional IMSI catcher world for a little while. He's going to give you an overview of that.
Yeah, so some of you guys were last year in Black Hat, that was in Amsterdam, so we had a talk on LTE-IMSI catchers. We explained some 4G IMSI catchers, how to build and all those. But now I'm not going too detailed, just to give introduction briefly about what with the conventional IMSI catcher, what they basically use. Now the title says Wi-Fi based IMSI catcher, so you may have a question in your mind whether you just track the guy or whether you also intercepting his data communication or call, for example, right? So basically all these IMSI catcher has a two purpose what they use. The first is purely about the tracking. So first they wanted to track the users. So this could be either targeted attacks or maybe just listening all the surrounding users and try to infer from the identity who belongs to whom. So there are multiple ways of, you could say targeted attacks or maybe just a random attack. The second is interception about, okay, now once you track the guy, you know his identity, you fix your target now, so what you could do from there. Now you can ask him to attach to your IMSI catcher like a Stingray device, and then you try to intercept his call or SMS. Now, of course, you need a backend support to let him feel that this is the right base station you are talking, and he doesn't feel any interruption between the call. If he feels something, of course, he gets alert that something is bad, which is happening weird. So there has to be a efficient connection to the backend telco provider via any means. So I'm not covering those means, but there has to be enough connection. There has to be a technical capability to connect to this IMSI catcher back to the telecom network, so that if the normal guy is making a landline call, he should be able to make a landline call or mobile call, for example, right? So the second part is about interception. So same goes apply with the SMS and as well as data connection. Now with the data connection, there is a possibility, I will come to the next slide with the 2G and 3G differences. And these IMSI catchers, of course, operates on the licensed mobile brands, frequency bands, and this could be GSM, 3G, and 4G. In the market right now, we have seen already GSM and 3G. There are some actually, if you Google, you will also find there are some IMSI catcher product which also says that they operate on a 4G brand, 4G frequency bands. But the problem is, okay, most of them claim they try to do downgrading. So basically, they just jam the frequency which is operate for 4G or 3G, and they ask you to come back to 2G. So as you may aware that 2G already has lots of problem. There is no mutual authentication, and easily you can be snooped using 2G calls, and it's way easy than 3G and 4G. So all the bands are available, but it's a matter of whether somebody is downgrading you or not downgrading you. And by definition, of course, what this Stingray device or IMSI catcher means, somebody just brings some kind of a device which acts like a base station. And nowadays, the base station size is not like a big which you see in the building. So basically, the smallest size in the market, or you may guys have some actually, if you live in UK right now, you can also buy this small, like a DSL modem boxes, which is like a base station basically. And you can also like small device, you can buy that device and convert into IMSI catcher. So size is getting really long. What it does basically just try to connect all surrounding mobile phones, which has a limited range, like a 50 meter until, depending on the RF capability of your device, and then you can ask the devices to connect you. And they operate in a two mode, which I somehow explained initially. So first is passive mode. Passive means you are just acting as a bad guy, listening on the RF, doing nothing. So you're just looking at the broadcast packets, what you can see, any identity or any parameters. Unfortunately, if there is no encryption there, you may see some extra information like calls and SMS, but depending on if there is encryption or not. So the passive guy can't really do anything, but definitely he can try to infer the IMSI, because again, now we are not going in detail because next Pierre will talk about the Wi-Fi, but in mobile networks, basically what happens, if you're getting a call, like an incoming call or data connection, what happens, the base station sends you the hi message, which contains your identity. So it could be the IMSI, which Piers already explained, or it could be a TIMSI, or like another term which we use in 4G called GUTI. So that may try to infer you, this is you guy. And this is what the passive IMSI catcher does. It just monitors everything on the RF side and try to infer your identity. So there are different techniques, which we explained last year. In the active style, then somebody just tried to bring the base station which tried to mimic as your operator. For example, you are using a Vodafone SIM card, and the attacker will set up this base station as a Vodafone. So your phone automatically sees there is a Vodafone base station which has a nice signal strength. And our phone is designed in such a way that as long as he sees a maximum power strength from the near base station, it will just try to connect to there instead of the base station which has a lesser power. So somebody can exploit that vulnerability. So somebody just bring base station near to you. So it will just automatically disconnect from the base station which is on the building, and it will connect to the attackers which is nearby. So this is like TMC catcher, and this can be used for intercepting your calls as well, because this has some capability to support the call functionality or internet functionality, and also to intercept your SMS, because you need to give the feel that the SMS is being really delivered. Of course, you could have in mind like, okay, I can bring an active base station and I will just intercept every calls and I will not deliver to the network, but that's fine. But the user may get alert that, okay, I'm making a call, everything, it's being ringing, but actually nobody's picking the call. So he may feel something weird. So it's about without detection. So what is the cost on those boxes? Basically, so commercial solutions are quite expensive if you wanted to buy like a special IMSI catcher. But now again, this statement is kind of bad if I say like this. Now, if you just Google Alibaba, you can just go on Alibaba or find any other commercial tools, Russian and Chinese, you may find that somebody's trying to sell for $3,000 or maybe until $50,000, and you can just buy these boxes. Originally, these boxes are only allowed to buy or sell for the government agencies, but now you can also buy those ones. Or you can build yourself with just a laptop, and there are lots of software-defined radio platforms where you can install open source software like Osmocom, OpenBTS, even the 3G version we have OpenBTS, UMTS, plus the 4G SRS OpenLTE you can install. So we have a different variant which are used for the research platforms, but they can be also converted into IMSI catchers. And this technology of IMSI catchers has been a long time, since 1990, and this has been patented, first time patented by a German company, Rode and Schwarz, which was back in 1993. So there are also already other patents about this IMSI catcher, which the way you track other people around that, so you can also look for the information. So before we head to the main talk, so just to give a difference between this 2G and 3G and what we could do actually there, and what is the flaw? Because now when we talk about this next Wi-Fi IMSI catcher, you will also see there are some kind of similar kind of a flaw we exploit basically. This is about the design, the way our mobile communication work, or authentication in the SIM card, or the way subscriber actually authenticated. On the 2G, we know that they exploit the protocol flaws where there is no mutual authentication between the base station and mobile phone. So this is like a existing flaw. This can't be fixed for 2G communication, unfortunately. So it allows for tracking and interception. Somebody can just bring fake base station and say, hey, I'm this guy and let's talk. Mobile phone can't do anything. And the saddest part in our side is that mobile phone is always act as a dumb device in a protocol communication. So whatever the base station tells, do this, it just accepts, let's do this. So this has been fixed in 3G and 4G. If the fake base station comes and, hey, talk to me in a plain text, it will say, no, I'm not going to talk to plain text, at least have integrity protection messages, at least it will use a key, integrity key to talk to each other. Of course, they can disable encryption, but there is a integrity key whether you can't read it. But this is only available in 3G and 4G, but not in 2G. So 2G is completely problematic if somebody brings a fake base station, and the sizes on the picture with this one. With the 3G and 4G, so again, they exploit the same architecture issues, like somebody can bring a fake base station, can get the identity, but they can't really have a key to talk to each other after the authentication. So still fine, but somebody can easily track. and difficult to intercept. And that's what the claim, because you see in media article, okay, somebody built a 4G IMSI catcher and they're trying to intercept. No, this is not possible, because you're not going to get the key which is used to talk to the communication. This key is only belong to the operator, and until and unless you have all the key material, you can't really decrypt anybody's calls or communication, even when you are using a 4G IMSI catcher. Commercial, all the products IMSI catcher, they try to downgrade you, or use of legitimate base station, which is also possible. Like in 2012 Black Hat, we had a talk about using a femtocell, which is like I said, small base station of 4G. You can buy this. This is like a small embedded Linux box, which you can compromise this box. You can just root on the box. You can try to circumvent IPsec communication, extract the key, and basically you see everything in plain text. And that's possible if you bring this kind of solutions for 4G interception, act as IMSI catcher. That's possible. On the picture you see, this is like a small base station which is used for the emergency purpose. So what this base station has, this has a back-end satellite connection. And if somebody brings this kind of solutions as a 4G IMSI catcher in the backpack, of course, then actually he can intercept every 4G call. That's complete. This is called a legitimate base station which has a back-end support of some operator. And now you may question, some shady operators may have some connection to do that. But now, okay, what is the protection on these IMSI catchers and why we have to look in the Wi-Fi, right? So there is no protection available for the phone which you're carrying in your pocket now. Like if you have an iPhone, you have an Android phone, you have a Windows phone, you have a BlackBerry, there is no such app can work effectively to detect this kind of attacks, like somebody is really tracking you or not tracking you. Okay, there are some special tools, there are some apps available, but the special phones can only act as an I would say some limited options you have there. So those are the phones which supports encrypted calls as well. They can have a special tools as a firewall for the baseband, which can try to prevent those threats. They can try to detect the silent SMS and all those nasty attacks. But those are expensive. The cost is really go until I don't know exact price, but the last time I remember from the price from the guys they mentioned of about $3,500 US or something around that. And there are some apps which we also develop at Cells. Like I had a talk in Black Hat 2014 about the app called Darshak. We developed that app to detect IMSI catchers, but this was only works on Samsung phones, Samsung Galaxy S3, which has an Intel baseband. And the later SR Labs in Germany, they also introduced an app called Snoop Snitch. So you can install those apps and try to detect the IMSI catchers, right? So this also works, but you need to root the phone, and not every normal user could do that. But now again, it comes to the back. So what is the protection? You can turn off your flight mode. You can go in a flight mode, and you can just use a Wi-Fi for all the communication, and you are still secure, right? And now this used to be a common threat, or this is the best protection somebody could suggest. So use like a Wi-Fi, or use multi-hotspot technology, like bring another phone and take this phone as a hotspot, Wi-Fi hotspot, and then connect your phone to this middle phone. Then basically, if somebody attacks, they can try to attack this phone, which doesn't belong to your identity, and then you can use your phone attached as a Wi-Fi. So basically, you had an intermediate layer which to talk there, or you can just use a Wi-Fi. But now Wi-Fi has a different things, and that's what we talk in this. That's what we try to introduce in this talk. Due to the convergence of all telecommunication technologies, and everybody just want to use now Wi-Fi calling or Wi-Fi features. And why this is just a technical terms about just before I hand over to Piers, because mobile operators are running out of so they try to introduce new technologies, because you don't get the coverage inside the house or inside the office buildings, right? And at that time, you can't use the normal mobile connection, or signal is so poor, you can't do. Either you introduce this small base station, or now they are supporting to use Wi-Fi to use your normal mobile functions. So you will be using Wi-Fi, but basically you will use all your billing plan what you have on a SIM card. And that's introduced some new threats, which now Pierre will try to introduce you with the Wi-Fi IMSI catcher.
Okay, thanks, Ravi. Yeah, so basically talking about the Wi-Fi based IMSI catcher, as Ravi mentioned, some of the conventional IMSI catchers provide for additional services like interception, but R1 provides for basically picking up, detecting the IMSI and essentially working out the location, potentially working out the location from that. I mean, typically, if you're going to catch the IMSI, whether it's a conventional one or R1, you typically need to be co-located with the target, and so you kind of know roughly where they are. But so our system allows you to basically extract the IMSI, but not actually intercept the calls. And it operates in the ISM bands, the industrial, scientific, medical bands, which are, in which Wi-Fi operates, typically in 2.4 gigahertz or 5 gigahertz. There's others as well. So the range is Wi-Fi range, although of course that can be extended. You see these kind of things people will stick in Pringles packets and all that kind of stuff to extend the range. I mean, it can be done with more sophisticated approaches, so you can get quite a bit more range out of Wi-Fi. Basically, it operates by, well, I'm going to go into the detail, but one approach is a sort of fake access point, and then the other technique is about either sort of spoofing, redirecting traffic to a operator data gateway. And we're exploiting weaknesses in the protocol and configuration to achieve this. So basically, as I said, the IMSI catcher is based upon two techniques. The Wi-Fi network authentication, which is one portion, and it's defined in this 3GPP, the mobile standards body, basically in standard TS 33.234. If you need to know the details, and this is how they refer to it in the spec. They call it WLAN direct IP access, and then Wi-Fi calling authentication is referred to as WLAN 3GPP IP access. And we've discovered issues in these two technologies. And the cost is of course, pretty low. Basically, virtually any Wi-Fi capable sort of computer. So anything from a laptop kind of downwards, Raspberry Pi. The Raspberry Pi 3 has a little inbuilt Wi-Fi these days, which is quite handy. So, just looking briefly at the Wi-Fi network attachment, sort of when a device, when a phone sort of tries to connect to the network, what kind of networks are there out there? Well, there's the sort of unencrypted Wi-Fi access points, no password basically, but then they often have something called a captive portal, which is the sort of little sheet that pops up when you try and connect to them, and they'll ask you for some credentials potentially, or just type in your email address or whatever it is. And that's typically based on something called Whisper, this protocol, although it can be based on a bunch of weird hacks as well. It's a bit of a messy area. Of course, they can just be completely open as well. Google, interestingly enough, Google's Fi service relies upon open Wi-Fi access points, it says, and it sets up a little VPN which they use, but it's not really available here. So we've had a brief dig into it, but haven't really found anything particularly interesting so far. Normal encrypted Wi-Fi access points, well, they're sort of pre-shared password credentials which are used to then get you connected. And then there's these auto-connect Wi-Fi access points. I mean, there are some in sort of like companies run them and things, but then there are different types of way the automatic Wi-Fi access points work, but specifically we're looking at these access points that are essentially managed, well, they're basically managed by the mobile operators, and they allow a mobile phone to negotiate, to basically connect to the Wi-Fi network automatically without any user intervention. And it does this by using the credentials in the SIM card, basically the IMSI and the key. And this is controlled by operator-provided configuration that gets loaded onto the phone. So it can either be users have to configure it manually, or there is some automatic type of configuration. So let's have a little closer look at those automatic configurations, because those basically mean that you just your phone, kind of without you particularly asking for it, will just, your operators configured the phones to automatically connect to certain Wi-Fi networks. So a lot of the big brands have their sort of auto Wi-Fi networks, you'll see they'll often sort of say auto AT&T or auto EE, or and then there are sort of more obscure ones, O2's Wi-Fi Extra and Vodafone Wi-Fi. There's a bunch of them. I mean, and they're quite handy because basically they allow the phone just connects to Wi-Fi and just you get sort of fall back to Wi-Fi, so you get faster data connection depending on where you are. But it works. It actually, automatic configuration is set up on actually a number of Android and Windows phones. Because if you look at some of the web pages for some of these operator offerings, they say that certain brands of phones, and it includes Windows, Android, and iOS. We've had a bit of a closer look at iOS. iOS also configures the phones based upon the inserted SIM, and it activates an operator-specific .mobile config file, and then that configures the device, depending on what SIM's in there, to have a bunch of pre-configured auto Wi-Fi lists in there. And we did a brief analysis of iOS 9 and found more than 50 profiles, nearly 60 odd profiles containing auto Wi-Fi type networks. There's also a bunch of other configuration in there. Manual ones, so some Android devices require manual config, so you basically have to follow the instructions on an operator website, and it's just pretty simple sort of stuff. You just tap on the network and then select in the drop down, like sort of SIM, it said, as the authentication technique. And then once you've done that once, then it then connects to that network repeatedly. And then Android also provides some additional carrier control mechanisms. In the sort of newer versions of Android, there are various sort of APIs basically coming out that allow for configuring of the phone based upon carrier profiles. So this automatic Wi-Fi authentication, having a closer look at that is sort of yet another standards body, the IEEE and 802.1x, which is port-based network access control, which basically defines the use of a protocol called Extensible Authentication Protocol, or EAP for short, which is defined by the IETF, the Internet Engineering Task Force. And that basically specifies transporting of this EAP protocol over the LAN, over Wi-Fi, or over like Ethernet or whatever. So it's called EAP-HOLE, EAP over LAN. Anyway, so there's rather a lot of those sort of standards kind of being put together. And in our case, looking specifically at what's happening when the phone tries to connect to the one of these auto Wi-Fi networks, it's based upon two particular EAP methods. One, the first one, EAP SIM, which is it's specified in an Internet Engineering Task Force standard, and it is based upon sort of GSM security model with some enhancements. So there, so it's actually slightly better than just the basic GSM approach, but it does have some issues. But it is currently the most widely used at the moment for phones to connect to the Wi-Fi networks. There is also something called EAP-ACA, which it's based upon 3G security, and that is starting to be deployed. That provides a stronger connection, but unfortunately, both of these have the issue that we've discovered, which we'll talk about shortly. The support for these protocols is actually implemented in Android, iOS, Windows Mobile, BlackBerry, so basically most of the world's smartphones. And we've been the good guys. We spoke to Apple and Microsoft and BlackBerry, and they kind of got around to replying and acknowledged that it was an issue. And Apple have been probably carrying the flag on it a bit. They did take things forward, and they actually developed a new feature to go into iOS 10 as a result of our discussions with them, something called conservative peer, which I can explain in a moment, which is basically due to the interactions we've had with them. So we've been talking to them for like over 6 months about this issue. And we've also talked to the GSMA, the GSM Association, which is basically represents kind of most of the world's operators. Gave a talk to them about the issue a couple of months back, and just sort of raise awareness there. But maybe because it's such a big issue, no one's really thinks, oh well, it's my fault, so maybe we'll do a privacy bounty or something like that. No one kind of quite feels it's they can stop it. So there's no kind of bounties involved in this work. But it's something that we're looking to try to get fixed. But it's a feature that's useful for most people. So it is being deployed in many countries, and the adoption is growing. So it'd be good to sort it out. So basically it comes down to the EAP SIM and EAP ACA, these two protocols I mentioned, the identities that are exchanged in these protocols. And there are three basic types of identity used in the authentication phase. And the one of particular interest is what's called the permanent identity, and which is, in this case, is the IMSI. And typically, the permanent identity is exchanged at the kind of initially, basically, when the phone first attaches to the network and tries to connect to the Wi-Fi, and after that, then there's going to be these temporary IDs, which are the next two. There's what's called a pseudonym identity, which is basically a kind of it's a pseudonym for the IMSI. So it's not the IMSI, but it's like it, and it has a sort of a lifetime. So then your phone then will send over the pseudonym. So then if someone sees that sort of flying over the wire, then they're not necessarily going to say that's that guy's IMSI. But then the protocol needs to exchange these pseudonyms and renew them, and so on. So there are some issues around using pseudonyms. Then there's another one called the fast reauthentication identity, which is a sort of lower overhead identifier. Basically, because the first interaction when you're using the IMSI, to actually do a proper check on it, your phone sort of hands over its IMSI, and then that gets handed into the network, and then the network then ultimately has to go to the kind of back-end system and sort of say, like, where is this guy's IMSI and where's the key, and let's do the proper cryptographic exchange. And so that's done on initial connection, but then you then get this fast reauthentication ID, which is then can then be used. So it can just be used in the sort of the more of the edge system, so they can then just cache that fast reauthentication ID and then do a quick reauthentication when you kind of come back. So like, for example, on the London Underground, you'll pop between stations and you'll have to reauthenticate every time. So it speeds stuff up like that. And walking down the street, there'll be multiple access points. You don't want to have to be talking to the kind of deep end of the operator-backed systems. So those are the three. And then the actual behavior is affected by what's called the peer policy. So there's the sort of current default is called liberal peer, which basically in this protocol, you can sort of say, give me your best identifier, and typically your best one, if you've got a fast reauthentication one, you'll send that one. And But you can also say, give me your permanent identifier. And with liberal peer, phone just says, sure, here's my IMSI. So, and it'll just hand it over. But with conservative peer, which is a sort of future deployment option, and it's part of it's in the spec, but it's not generally been implemented. But it has now been implemented in iOS 10. Although, I mean, it may be in Android in some of the newer versions, but I've been in touch with Google, but they haven't specifically mentioned it. Conservative peer only responds to requests for permanent identity, as in your IMSI, when there's no pseudonym identity available. So it basically makes it a bit harder to extract the IMSI from the device. So how is this actual conversation that we've been discussing? How does this EAP SIM work? Like, what happens to the packets? And typically, EAP is a general. There are lots of EAP sort of methods, and it's an authentication protocol. It exchanges sort of kind of basically some kind of credentials, and it's not encrypted. It's not encrypted sort of interchange. And currently, EAP SIM, EAP ACA, when it's run EPOL, sort of EAP over LAN, this 802.1x, the way that it's deployed at the moment is, unfortunately, it's unencrypted. So thus, the IMSI is visible to a passive attacker when a permanent identity, the IMSI is used for full authentication. So on initial connection, and then it's also, it can be revealed if there's an active attack, basically by requesting full authentication, which are the two sort of uglies on this one. So it means that that can be obtained, and we have we've tested this out. But I mean, you'll be happy to hear that, as we mentioned earlier, the actual content is still protected. So although one can get the IMSI, you can't actually, and you can observe the whole interaction, this authentication interaction. But like with a few, most cryptography, you can look at the sort of cryptographic interchange, and you can't actually work out what's being said necessarily. And the key exchange process is designed so that the keys aren't actually transported in the clear. They're negotiated at each endpoint and retained there. So content is still protected. Now there are systems, basically protocols that can allow for protection, basically encryption of the interchange. Like, for example, EAP TTLS, or TTLS v0 as it's typically, as it's currently sort of defined, and EAP TLS. They are potential ways of protecting it, but they do then require support in the mobile OS and the operator and all the vendor systems so that it can be deployed. So that's the first approach sort of covered, and I'll give a demo on that. So basically, the IMSI can be revealed in this interaction when a mobile phone tries to connect to a Wi-Fi network that has this, which is configured to use this EAP SIM or EAP ACA in the current configuration. So moving on to the next one, the Wi-Fi calling connection. So what happens here? When a phone is using Wi-Fi to make a call, this is the Wi-Fi calling stuff that's actually built into the OS typically. So iOS has sort of had it for a while, and I believe Android has had it for a while, and I think Windows have had it too. but it's sort of starting to rise in terms of deployment and usage because it, as Ravi mentioned, I mean, it provides sort of offload, and in black spots and stuff like that, you can use Wi-Fi. This is different from all the sort of over-the-top apps like whatever, WhatsApp, Signal, all the rest of them. This is actually working with the operator. So what happens is the phone attempts to connect to something called the Edge Packet Data Gateway over Wi-Fi. And it can make voice calls over this connection. And the phone will attempt to connect to the Edge Packet Data Gateway when it's in areas of low signal, or it will also connect when it goes into airplane mode, and then you flip on the Wi-Fi, interestingly enough. And that's what I'm going to show in the demo. So the connection to the EPDG uses something called IPsec, this IP security protocol, which people are probably aware of. And there's an exchange at the beginning of most IPsec connections, which is called to do the authentication and key setup. And the particular protocol used there is called IKE, Internet Key Exchange Protocol, version 2 right now. Version 1 was a few years back, had some problems, so they had to cook up a new one. So, and this is, as I said, supported iOS, Android, and Windows, and Wi-Fi calling available in a bunch of countries. And again, we've mentioned this one to the OS guys and to the operators, and they're sort of aware of the situation, but it is a bit of a systemic kind of thing. It requires a bit of work. So anyway, let's go into the details here. IPsec brief overview. It basically provides for authentication confidentiality with these two AH and ESP for doing, is actually encrypting the payloads, encrypting the voice. Key management is then done by there's something called IKE v2. And you've got two modes. You've got what's called a tunnel mode, which is used for connection to the gateway. So like any packets from, well, potentially different entities on a network can be sent through a tunnel. You have transport mode, which is just direct point to point. So what happens in this internet key exchange? Well, there are two phases. There's something called the IKE SA init, which negotiates cryptographic algorithms, exchanges a bunch of stuff like nonces and everything, and does something called the Diffie-Hellman exchange, which basically sets up a key pair to encrypt the following exchange, the IKE auth exchange, at which point identities are exchanged. In our case, in using EAP ACA in this case, so the IMSI is being transported. Now, it is encrypted here, but unfortunately, this initial exchange is not actually protected by a certificate right now. So you can set up a man in the middle and basically pretend to be an EPDG, and the phone will connect to it, and then it'll basically say, "Here's my IMSI." So another. All right, yeah. Basically, that is the second issue. So the IMSI is then revealed in this situation as well. So it's basically two separate techniques to extract the IMSI from smartphones. The actual call content, again, is still protected, so it's just an identity attack. So what kind of mitigations are there? Well, I think one of the things that I think is would be good to sort out would move off of EAP SIM as default and move towards ACA, because EAP SIM is weaker because it uses some of the GSM cryptographic technology, which isn't quite as strong as the EAP ACA approach, but there aren't any widely known sort of attacks on it. The other thing is to deploy this conservative peer mode of operation using, well, potentially with EAP SIM even, but preferably with EAP ACA. And then looking at a certificate-based approach, which you would then require investing in putting certificates into the AAA infrastructure, and then it would then provide for protected tunnels for the EAP ACA, for waveLAN access, and for the Wi-Fi calling. So basically using this protocol I talked about, EAP SIM, EAP TTLS plus EAP ACA. Then there are other, looking at other potential solutions like encrypting the IMSI, and then there are other sort of standards that have been mentioned as possible ways of protecting the IMSI. So it really needs the sort of standards bodies to take another look at this. Because there are kind of solutions in there, but they're just not really being deployed, and they're more expensive to deploy, I guess. But then it depends on how much you feel that should be protected. So mobile OS mitigations, well, we need to support some of these protocols that we're talking about. So conservative peer pseudonym support, and then you've got to support the actual certificate-based approaches, implement those in the OSs. And then the other thing which would be nice is to allow a bit more user choice over automatic Wi-Fi network access, which currently is a bit tricky, preferably allowing for editing of all stored associations. So what can you do? User mitigation? Well, with iOS, you can go and actually, if you're near one of these automatic Wi-Fi networks, you can actually tap on the thing, tap on the little eye, the little info thing, and then say don't auto join. And then, as I mentioned, the conservative peer in iOS. Android, we've got you can forget the settings there, and for the auto Wi-Fi again similarly. And you can selectively turn off Wi-Fi calling if you want on the phone as well. And in untrusted environments, probably not a bad idea to turn off Wi-Fi. Summary, so we've got these two points where we've found weaknesses. Most of the world's smartphones implement these protocols, but these techniques rely upon the installed operator configuration so that the phones are actually automatically trying to connect to these services. They don't do that necessarily by default, but the major operators do provide that config. So we've been working with these guys, but it is a complicated issue, so it'd take a while. So we've been doing this, going to look into more stuff. We've been doing this under this 5G Ensure European project, and we're looking further into these things. So I'm just going to give a quick demo, and whoops, see if we can slide our way out of here. So what we've got here is, whoops, I'll turn that off for now. Now, what I'm going to do is I'm going to do the Wi-Fi calling IMSI catcher. So what this is going to do is going to set up little access point running in a virtual machine on the laptop. So I can run up Wi-Fi, and then it'll show a bunch of. So now we're then going to kick off the Wi-Fi calling IMSI catcher, and we'll see in a second that the phone, let's just give it a full scan. Right, so where are we? There we are, this little guy here, Wi-Fi calling. So I'm going to tap on that one. I'm going to join my, this one, sort of just simulating an access point, so we've got to wait for the tick. It obtains an address, and then I'll bring up, there we are, so we've got the tick, so we're connected to the network. Oh, and there, straight off, we see the the IMSI. Now, I have sort of obfuscated that one, so that's the one from the slides, but it's basically a script where I'm just dumping it, and it's there trying to connect to the Wi-Fi calling server, and I'm doing a man-in-the-middle attack on the phone, basically, and running a fake endpoint, and then dumping the IMSI there. So then I'm going to do the Wi-Fi network catcher. So now you'll see that the Wi-Fi calling, whoops, it's trying to connect to the purple. Now, let's kick this guy off. Now, what we've got here is we're creating a bogus access point, which is going to be which is sort of pretending to be a sort of a network that is going to steal the creds for the Wi-Fi network authentication. And we're running Wireshark here in the terminal to dump the traffic. Now, this guy is...
And the Wireshark is running on the monitoring mode.
Yeah. Currently, this one is not being found. Sorry? Sorry, say again? Yeah, it's a bit of a tricky one, isn't it? Yeah, I can make it a little bit bigger, but it appears to be, unfortunately, not.
Okay. I think she'll be fine.
This one is, unfortunately, not working, sadly. I do have a demo of this one, a little video.
Okay, so...
Oh, there we are. Got it. Right. There we are. See, I'm running a Wireshark for those sort of you familiar. So you'll then again be able to see it is connecting. Well, it doesn't always show you on the screen, but what it does is it automatically tries to connect to networks that it knows. So this one I've called as Auto Eat Wi-Fi. So it then tries to connect, but then it fails. But in doing so, we're dumping the EAP interchange, and you can see this is just running, as Ravi said, in monitor mode. So it's just capturing the traffic flowing over the network. So there's no decryption being done here. So we see again the IMSI revealed.
And actually, what's the biggest threat here, what he mentioned, or just now we finished in the slide, like you have an iPhone, right? Everybody has an iPhone. So actually in your iPhone, all these profiles, like what he mentioned, under Wi-Fi calling, are actually locally stored by default by the Apple actually. So you can dump out those database and he can set up his laptop as an access point. So all your iPhone, which already have this profile, will automatically connect to this Wi-Fi without even asking, as long as your Wi-Fi is on. You don't need to click on connect. And if you just have Wi-Fi on, basically he can just take everybody's IMSI and can show it here. This is only badly affected with iPhones actually, and this is the biggest problem for the iPhone.
I did notice that it is also automatically configured on a bunch of Android and Windows phones.
Yeah, so it's basically a thread that you don't notice that this is happening in the background. So you can't really control on that.
So as you saw, my phone automatically connected to that EAP SIM access point. I had set it up previously to the demo, and before it was sort of connected to another network, but it tries to connect, and we were doing the packet dump, and you could see it connecting to that network. So those are basically the two issues, and we have been working with vendors and mostly operators and OS people to try and move this forward. But I think it becomes a point where you have to sort of spread the word a bit further to sort of see that there is actually an issue here, and it should be fixed. But it's a complex issue, so it's not like you can't just sort of say go patch that little bug. It's a question of getting the standards right and getting people to implement those and deciding that it's actually worthwhile. I mean, I guess at some point, it's this actual sort of vulnerability, if you like, is written about in the standards. They say it's a possible issue. Identity compromise is mentioned in the sort of security considerations, but I think it's also about how technology's moved on and how easy it is to get hold of these things now. I guess some of these standards are getting on a bit. EAP SIM is from 2006, so there's well, maybe then they thought it was just that bit more difficult for people to do that sort of thing. I mean, I guess it was definitely the case with mobile spectrum, and now you can buy kind of SDR kit for a few $100s or less, buy the old RTL SDR for like $15 to sort of passively sniff on some of the mobile spectrum. So it's all become a lot cheaper and more easy. So then consequently the sort of security solutions need to sort of move up as well. So I don't know if anyone has any more questions, apart from the font size.
This is the way you can reveal the IMSI only. There is no way to get the IMEI from the phone.
No. I mean, yeah, you can get the IMEI if you do like a sort of a 2G kind of conventional IMSI attack. You can't get it there. I mean, not right now. We haven't come up with a way.
So this way you get the MAC address of the Wi-Fi.
Yeah, I mean that's the thing. I mean, you can potentially you can link. It's a sort of linking. You can potentially link the IMSI with the MAC address, which is something which is.
But the
that's
IMSI
become a problem.
Yeah, sorry. The IMSI is actually, there are other ways to interact to confirm your phone number. You can't link the MAC address with your phone number. That's the problem. But IMSI can link with the phone number and with the guy. Public information.
Yeah, and you can then so a SIM card might be moved from one device to another device. So you can then sort of track it through that way.
Yeah.
There's no content interception with either of these techniques, just threat.
Can you repeat the question because it's on mic?
Yeah, no content. There's no content. No, you can't obtain content from this technique. No, just the IMSI.
So one last question here.
Yeah.
Those countermeasures you proposed in one way or the other use certificates or certificate-based approach. Have you ever considered how this might work in roaming? Because, I mean, it's easy if you have one operator, one phone connected or phone connected, but in roaming scenarios, you would need those certificates from roughly 800 operators. So
it does start to get complicated. I mean, the thing is with Wi-Fi calling, you're typically connecting back to the Edge Packet Data Gateway run by your own operator. So they'll have the certificate there, you'll have it on your phone, so you won't have necessarily an issue. You'll just be traveling over the internet. But with the Wi-Fi network stuff, you may have an issue, but there are some solutions where potentially the authentication would be pushed back. Then you may want to develop some acceleration techniques for localized sort of caching of creds and stuff. But I think it's possible, but it does make it more complicated. Yeah. The introduction of certificates, and potentially, more certificates you spread around, the more potential there is for someone to go and steal the certificates, and then they can then use one of those stolen certs to then kind of like spoof another sort of supposedly legit endpoint. But I guess it kind of raises the bar, but it does raise the bar in terms of cost as well. So it's a tricky game, and also it's like what CAs do you rely upon? Like you're probably not going to want to rely upon the entire sort of stack of CAs that's in most sort of OSs today. You might want to have a separate operator store or possibly in some more protected storage. But then it's updating certs if they become compromised. There are all those issues then you have with certificate-based security. Yeah.
Okay, so I think we can take the question offline because he wanted to kick us off now. Anyway, for the next talk, yeah, we can take it offline.
Right.
Thank you.
Thanks very much.